Okay, students, today we have two concepts. We're dealing with quadrilaterals right now. And I've given you a quadrilateral hierarchy note sheet. That's what we're going to use on here to identify the most specific name. As you go down the sheet, that becomes more and more specific. I have drawings on them. Some look just like the drawing on there, so it's easy to tell what it is. Here, it's making sure you know the same idea up here, but with angle with numbers instead. You're going to get one or the other of these on the decast, so you have to know either if they give it to you by numbers, what the shape is called, or just by the markings. Okay. Down here, you're going to state all the possibilities. So if you look at your sheet, you can see that's a square, so that therefore everything from the square up would satisfy. Okay. Here, parallelogram, so parallelogram up would satisfy those conditions. Okay. Backside, that's where we're going to focus. Okay. So we're going to find out, these are all regular polygons. Regular means equilateral and equiangular. You've had that word before, so if you need to write it down again, write it down. Regular means equilateral and equiangular. Angular. Okay, that's a word that you have to know for the decast. Okay, and we'll be using it all throughout here as well. And I'll review it for extra credit, see who has it memorized. Okay. So as you can see here, all these polygons are equilateral and equiangular. Okay. Now, the other thing I didn't, and I pointed out in class, is the definition of polygon. A polygon can only be made up of segments, not curves. So therefore, a circle is not a polygon or a semicircle, anything with curves on it. It can only be made up of segments, and the segments must intersect at their endpoints. So as I pointed out in class, here's an example. We have all segments here. Those are 3 segments, but this is not a polygon, this triangle, because it does not intersect at the endpoints. So in order for it to be a polygon, oops, let me get rid of that. In order for it to be a polygon, the segments must intersect at the endpoints. So now, let's see if I can get it to make it right there. So now this is a polygon because the 3 segments intersect at their endpoints. Okay. We also talked about, and the only type of triangle or polygons that we talk about are called convex polygons. So on the board I drawn what is called a non-convex polygon. Non-convex polygon, again, it is made up of, let's just erase that. It's made up of only segments. The difference is this is called a non-convex or concave polygon, because if I was to extend any of these segments, so this, if I extend this segment, it comes inside the figure. So that's non-convex or concave. When I extend any of these sides, they remain outside the figure. So this is a convex polygon. This is a non-convex quadrilateral. Okay, because I extend one of these sides, in this case it's both of these sides. It only has to happen once. Okay, but if it happens, then it's concave, and so we can't do angle measures in different formulas with concave or non-convex polygons, only with convex polygons. So that's all we'll be working with. And that's all these are right here. Okay, so that's just some vocab on the side there. All right, so we want to find the sum of all the interior angles. If we were to extend one of these sides, we're going to be doing number 4 down here. You can see I redrew it down here. Okay, that's the example I did in class. So we're going to find the sum of all these interior angles. We're going to find what each one of these is exactly. They're all the same, or equiangular. So that's going to be the interior angle, finding what one of them is. And then we're going to find the exterior angle. They're all the same there. And that can be done in one of 2 ways, which I'll show you down here. Okay, so the formula for the sum of all the interior angles of a convex polygon. Remember, we're only dealing with convex polygons. The name of that is called the polygon sum theorem, and that formula or expression is n minus 2 times 180. N meaning the number of sides in that polygon. So in this case, we have a hexagon here, 6 sides. So n is 6. Now, so where does this formula come from? Well, n minus 2 represents the number of triangles that can be drawn within this hexagon from any one vertex. So when I connect, I chose this vertex to use. If I connect what are called diagonals, drawing the diagonals from this one vertex, that means to connect that vertex to any vertex it's not already connected to. So it wasn't connected to that one, it wasn't connected to that one, it wasn't connected to that one. So these are the 3 diagonals that you have from this one vertex. Well, notice that creates 1 triangle, 2 triangles, 3 triangles, 4 triangles. And we know every triangle is 180 degrees. So that's why it's n minus 2, because you'd always be able to create 2 less triangles in your polygon than the number of sides itself. So 6 minus 2 is 4. As we see right here, times 180 is 720 degrees. So total degrees, that's the sum for number 4 up here, would be 720 degrees. Now remember, since they're all equilateral and equiangular, to get any one of these angles, I just take that 720 degrees divided by the number of angles, which is 6, and I get 120 degrees. So that's the answer for the interior. Each interior angle here is 120 degrees. How do I get the exterior? The exterior would be, for example, if I extended one of these sides out, let's just draw that out right there. Okay, well, we just said that this right here was 120 for the interior. Okay, so then easy to see, doesn't this form a linear pair right here? So therefore it's 180 minus 120, which is what you see right here, and that gives you 60 degrees. So the exterior is 60 degree, exterior angle for each one of these is 60 degrees. You can also get that by, as it says here, or 360 divided by n, or so n was 6 sides or 6 angles, 360 divided by 6 is 60 degrees also. And as it tells you as a final note here, the total degrees of all exterior angles is always 360. So if I add up the exterior angles, it's always going to be 360 no matter how many angles there are. Okay, doesn't matter how many angles there are in the polygon, the total degrees of the exterior angles is always 360. So to get that angle, you can just do 360 divided by the number of angles, or I can create my linear pair after I find out my interior angle, and then do that. Now, if it just asked you, the only question it asked you was the exterior angle, it didn't ask about interior angles or total degrees, so it just asked what's the exterior angle of a regular hexagon, I'm going to use the 360 divided by 6 and get the 60 right away. Okay, but if it asks me to find the interior, then I've got to do the total degrees first, divided by the number of angles, and get that, and then obviously it's easy to do a linear pair from there to get the 60 for the exterior angle. All right, that ends it for this lesson.